Okay, can you hear me? No problem. Is it on? Hello, hello. Hello, hello.
It's clear, Edward.
Okay, no problem. We will start the presentation. Okay, thank you. Hello, everybody. This is Edward speaking from the RIGOL Technologies. Today, I'm glad to share some comprehensive topics about the RF microwave technologies. So today, we will focus more on the port extension methodologies for the component test calibration challenges. Yeah, because as you know, the RF microwave, when you do the network analysis test, the calibration procedures and the accuracy is more important because it will directly impact your test result. So today, we will focus on how to validate the passive component by the network analyzer and leverage the applications to the calibration techniques of the port extension. Okay, so now we will extend it to see the presentations. What is the agendas? Okay. Okay. Okay, sorry. Yeah, no problem. Yeah. So today's agendas, we will focus on the 4 parts. We can separate it for 4 topics. The first one, we will focus on the market and applications of the network analysis. And of course, the second part, we will go through the basic principles of the RF microwave network analysis. And the third part, we will go for the highlight point of these topics about the port extension methodologies for the calibration techniques. And then we will switch over to the live demonstration by the RIGOL's RSA 5065 N series signal analyzers with the network analyzer options to have you a brief demonstration of the port extension methodologies. Okay. Finally, we will go through for the question and answer sections. If you have any questions, we can go through for it. Okay. Now we will go for the first one. So the applications of the vector network analyzers is very comprehensive because you know for the RF microwave communication systems, all the components, these assemblies inside the systems, all needed to use the network analyzer to do the component verifications, especially for the S parameters or impedance matching, or check for some kind of signal integrities qualities test, such as the base station communications of the mobile phone communications, right? And for recently, the hottest topics about the automotive, some kind of topics like the electrical car, because we have some kind of communication techniques through the wireless communications or near field communications, all the RF microwave, the wireless communications, we all need to use the passive components to hook up all the components together to build up the whole system. And the IoT is Internet of Things. The topic will go through for the several years since 2019 to 2024. So it is also coverage from the mobile phone communications narrowed down to the near field weak signals of wireless communications. And of course, because currently we focus on the 5G communications, but for the next stage, if you combine the mobile base stations infrastructures with the lower orbit satellite communications in the space, that means we will develop up to and upgrade to the 6G, the communication generations. So all kind of communications all need to use the network analyzers to do the component or subsystems verifications in advance. Okay, so now we will go through for what types of devices are tested. So the network analyzer is a very general instrument which can cover from the passive components, go through for the subsystems, and then go for the active components instead. So you can see the right-hand side of this presentation slide. You can see the left side is for the passive component, and the right-hand side you can see this is the active ones. So for example, if we want to test the passive component, it is major parts which covered more than 80% the components cross through the whole RF microwave system. For examples, like the transmission line, right? So the transmission line, that means the traveling wave will be guided inside the medias that is between the signal line and the ground. So the electromagnetic wave that we also call it as a traveling wave will be guided inside the transmission line. And for example, like the waveguide, like the mobile phone base stations, if you want to travel for some very high frequencies, high for the frequency, the signals, we need to use the waveguide to transit the electromagnetic inside the two-dimension or three-dimension waveguide. And the resonators is like the filters, because we can catch up with some specific frequency of the RF microwave signals and to retrieving this dedicated frequency outside for the dedicated transmission. So it is belongs to the filters. And for the subsystem like the mixers or the active devices like the amplifiers, for the amplifiers, we can also use the multi-port, the network analysis tools to do the amplifier tests like the gain, right? So if you go through the signals from the amplifiers, that means we can amplify the signals for several times of the voltage or current. Yeah. Okay, so we'll go through the next stage. So what is the network analyzers? So for the traditional network analyzer, for the network, that means not like the networks for the Ethernet network, because network means the electrical network inside the passive or active electrical component. So because the network, that means the electrical network for the transmission or reflections from the left-hand side port or the right-hand side port, both. Yeah. So we can also separate the network analyzers for two parts. One is the scalar type, and then the other one is vector type. For example, if we set the scalar type network analyzer, that means it analyzes the network, the power or voltages just by the magnitude or the scalar parameters inside the instrument. So there's no phase or vector type of parameters to be analyzed for furthermore discussions, like the phase or group delay or phase delay. So for the scalar type, it just measures the loss. or the transmission loss or the reflections, fractions of the powers, okay? For the vector type, that means that we can include it, the phase informations. So that means we can do some advanced analysis by the Smith chart. Of course, after this one, for the several pages, we will introduce more about the Smith chart. And also we can do the polar chart for the group delay or phase delay, so that can coverage the phase information in advance. Okay, so that is the basic categories of the network analyzers can separate for the scalar and vector type. So it is a basic concept we can leverage back to the basic optical analogies to the RF microwave energy. So it is quite the same structures. For the above one, you can see this is a lens, optical lens system like this one. So we can sending a light from the lens side. Some light will be transmitted through this lens. That means we can get transmitted signals here by the right-hand side. But some kind of the reflected wave or reflected light will be reflected by these directions. So it was also included the reflected ones and transmitted ones. So we can equivalent to the electrical network. If we, for example, like this device on the test, if we, like this one is a cable, RF microwave cable, okay? That means if we're sending a traveling wave from the right-hand side by the transmission line, so when we hook up this port to the left-hand side of this DUT, that means that some traveling wave will be transmitted through this DUT, and some kind of the traveling wave will be reflected by these directions. Okay, so it is quite the same, or the equivalent methodologies or the infrastructures can leverage with each others for both optical or RF microwave infrastructures. Okay. Yeah. So like in this one, so why do we need to test components? Because it is a very complicated transmission performance, because we need to do some high quality performance, especially address for the very high frequency, like the terahertz application, millimeter wave applications. Some kind of applications can coverage from the 30 gigahertz to several hundred gigahertz. So you know the very high frequency, that means that we can have less dynamic range or the very noisy background noise. So we need to calculate the S parameters for some kind of the like the power or the transmission efficiencies more accurate. So we need to use the network analyzer to do more accurate tests or validations in advance before we assemble all the components up to the system levels. So we need to use the network analyzer to verify all kinds of the components in advance. Okay. So the both magnitude and phase are more important because for the left-hand side, you can see this is the basic electrical network. So we can separate it by the induced by the S parameters concept. So what is S parameters? S parameters, that is the scattering parameters. Because you know the traveling wave or the signals from the left-hand side to the first port, like this one. If we get the reflection wave from the port 1, that means that we can get the S11 parameters here. That means the last one is transmitted the port, and the left one is received the port. So that's S11. That means we transmitted the signal from the left-hand side and get the reflected wave also from the first one port. So that means you can construct the S11 parameters. Okay, so you see this one, okay, so you see here. So the S21, that means the 1 is from the first port to transmit the signals to the device on the test and get the transmitted signals by left parameters here. So the 1 to 2, that means S21, that means from the 1 port transmitted to the 2 port. Okay, so we can get the loss information, right? Because the transmitted signals divided by the input signals, we can get the transmitted coefficient. So we can get the loss information here. Yeah, okay. So it is equivalent to the 2, and the 1, 2. So it is like a matrix. So S11, S1, 2, 1, and S1, 2, and S2, 2. This is diagnosis lines. So it is a symmetric. So it is equivalent in the symmetrics at this matrix. So it build up the S parameter or scattering parameters concept of the network analysis basics. So it is quite important. You need to know this basic. Okay. Yeah. So the other type is a Smith chart. So I will go through for the basic introductions for the next several pages. Okay. So for the network analysis, we can also do the time domain characteristics because the network analyzer is the RF frequency domain measurement. So we can use the inverse the Fourier transform to get the frequency domain informations back to the time domain. So that means we can also do some time domain analysis like the TDR, the transmitted time domain refractometry. Yeah, so we can get some fault distance or some fault point around the cables or the long distance cables characteristics verifications by using the TDR functionalities. Okay, so it is basic information about the magnitude and phase of the network analysis. Okay, for the second part, we will go through for the principles of the RF microwave network analysis. So it is a little bit complicated, but I will do my best to simplify the explanations as easy as possible. Okay, so you can see this one is a basic network. So it is port 1 from the left hand side and port 2 from the right hand side. So it is the forward reflections by S11, right? And the left hand side is S22, like this one. So we can also get the S21 from the 1 port to 2 port, or get the S12 from the 2 port reverse back to the 1 port, right? So that means we also call this as a S11, S22, S12, S21 matrix here. So this is isotropic media for the supposes, so we can get more information from the S parameters. So this is the electromagnetic theories about the transmission line theories. So you just can see the formulas go through it simplified. Okay, so you don't need to remember this formula. So you can see we need to focus on this one is the reflections coefficient. So gamma, right? So it is a refracted wave. Oh, this is reflected by the incident wave. Okay. This is a typo, sorry. And we can get the coefficient of the reflection coefficient and also get the phase information. Okay, and also get the return loss by the -20 to get the logarithm of this reflected coefficient. So it's quite simple formulas for basic. Then we can also get the VSWR. You know, the VSWR is the voltage standing wave ratios. It is very quite popular because if you want to verify the antenna, right? So today, for the next sessions, I will go through a live demonstration by using a device on the test of the antenna to let you know how to do the network analysis and measurement by the port extension. Okay. So this is the basic concept of the transmission line concept. So this is quite important because all the network analyzers all need to use the Smith chart to verify the impedance matching status when the R&D engineers or the design guys will want to verify the matching status about the impedance. Okay, so we can see the left-hand side, it is a Cartesian coordinate system, right? So the horizontal, we can see this is the real part. That means because the impedance, we can separate by the real part and the imaginary part, right? So the real part, that is the real resistance value, right? But for the imaginary part, that means some kind of impedance will be caused by the inductance or the capacitance, right? Yeah. So the real part, that means is for example, like the transmission line, that's just copper lines, the resistance. But for imaginary part, that means we have the dielectric, so we have a capacitance effect, or the long distance will induce the inductance effect, right? So if we bordering this Cartesian coordinate systems, so we can get this impedance chart. Impedance chart, we can also call it as a Smith chart, okay? So you can see the right-hand side, this point is the open point. And the left-hand side, this point is the short point. And the central part is the matching point. So the matching point, that means we don't call it as a 50 ohms because you don't know how much impedance the customer want to design for. Some kind of systems have the 50 ohms or have the 75 ohms or the 100 ohms, right? So if we normalize to the 1, so that means the central point is the matching point, is the normalized point, okay? Yeah. So you just need to remember this 3 points. That is okay, okay? Another side is the upper side of the circuit. That means the characteristics of this device on the test belongs to the inductive. This is inductive. For the below side, the lower upper, the semi-circle side, that is the capacitance effect. Okay, so that is very simple because impedance, the inductance we can generate by the J omega L impedance, right? If we causes the capacitance impedance, that means the J omega C 1 over the J omega C, right? So this is also can call this as a minus J omega C, right? So you can see this minus part, that means we have the minus imaginary part have a lower upper cycle. But for the omega L, that means at the upper semicircle, right? Okay, so it is very simple concept from the Smith chart. Okay, good. So this is a formula. I will not introduce more detail because you know that we can get all the coefficient and get the minus 20's logarithm can get the transmission coefficient or the reflective coefficient. So we can construct it the S parameters by using this formula. Okay, so we also can use the formulas to get the group delays informations and the phase shift informations like this one. Okay. Okay, this is a group delay. Group delay, that means that we can analyze more about the whole electromagnetic wave transmission behavior inside the waveguide or transmission lines. So this is the basic formulas. I will not go through it. If you have interest about this one, you can discuss with me after the presentations, or you can check for textbooks about any kind of microwave textbook or the electromagnetic wave theory. Okay. Yeah. So That's one is the Fourier inverse, the Fourier transform, that is the distance to fault. That's also called as a TDR refractory, because if we want to use this one to check for the cable's fault distance, like here, that means we can use the inverse Fourier transform, right? To get from the frequency domain back to the time domain, so we can verify by the time domain signal behavior. So by the signal behavior, that means that we can use the velocities, times the propagation speed. That means the propagation time, that means that we can go the whole distance, right? So we can get the resolutions and the positions like the Swift point. So if the velocity times the traveling time by the round trip, right? So we can divide it by the 2, that means we can get the distance from the departure point to the end of the fault distance, right? Okay, so this is the basic principles of the TDR principles of the time domain analysis of the network analyzer. Okay. Okay. So for the second part, the final one is a calibration of the vector network analyzer. So the calibrations is very important when we do the measurement of the VNA, because sometimes one engineers waste a lot of spend much of time. Sometimes if we do some very complicated calibration procedures, it will be spent several hours. For example, like previously, I used to work at the lab to calibrate for 100 gigahertz network analyzers. We use the probe stations to probing the semiconductor wafers. So we use the calibration plate and spend over 20 hours. But if you get a successful and the precise calibration result, the test procedures only 1 minute. Yeah, so you can see how important that calibration procedures is very important compared to the test procedures. Yeah, by the network analyzer. So you know the calibration procedures, we can include it the open short load calibration kit, or if you have the 4 port, you need to go through for every port the open short load calibrations, and through if you want to do the loss measurement or DTF, the TDR, the measurement. So you need to do some kind of very complicated calibrations. Some vendors also provided the eCals can save your time to do the calibration procedures, especially focus on the multi-port test. Okay. Okay. So we will finish the second, previous 2 sections of the presentations. So now we will go to the third part of the port extension methodologies of the calibration techniques. So it is quite important, because why the port extension is very important. You can see this diagram, okay? Because it is a network analyzer, right? But network analyzer, we have the port 1 and port 2. But it is impossible we hook up the devices directly to the port, right? Because some kind of customers' device on the test is very large, or the long distance, right? Behind and between the network analyzers. So we need to use the cable, right? To extend the test port to the device on the test here, right? So that means this cable is the extended media or the transmission media from the original calibration plan to extended the calibration plan to the cable's end of the port, terminal this one point, right? So that means that we need to calibrate the previous residues of the capacitance or the inductance effect of this one, and also we need to calculate to eliminate this cable effect, right? So that means we need to input some of the cables parameters to the vector inside the vector network analyzers to do the furthermore the mathematical calculations and more complicated calibration procedures to make more precise calibration result, right? Okay. So that is the major spirit of the calibrations of the port extension. So this is the basic residual effect from the whole test system. So we can introduce it for the basic concept of the transmission line here, right? So if the transmission lines like here, that means transmission line. What is transmission line? That means it is because if we treat it as a DC circuit, for traditional DC circuit like this one, for example, like this is the resistance, like this one. So this point have the same voltage level, here and here, right? So it can treat it as the same point. But for the transmission line theory, this point and this point is not equal voltage, equal potential. That means because it has a traveling wave here, right? So that means sometimes we can get the high voltage here, but we can get the lower voltage at this point, right? Because the traveling wave is very high frequencies. So the scale is very shorter than the whole transmission line length. So we need to treat it as the transmission line effect, okay? Yeah. So we will introduce more about this one. So yeah, you can see we can separate this by modeling as the lumped devices. Yeah, right. So so this mushroom, yeah, is a residue, right? Affected by the network analyzer. So we need to use the calibration software to eliminate this mushroom effect. Okay. But for the transmission line, we can simulate it as the equivalent lumped circuit as many R, L, G, C parameters like this one, right? So you can see this is lump 1 or lump 2N, right? So we can calculate it by the wavelength of the traveling wave. So average speaking, we need to use the 1 divided by 6, the 1/6, yeah, the wavelength, so we can get the equivalent lumped circuit devices. Yeah. So to make the more confirmed scale, we need to by 1/10. That is make sure you can get the more equivalent lumped circuit models by 1/10. Okay. So this is distributed circuit by the traveling wave concept. So you see, this is very important because the phase velocity here. So we need to input the entry, the dielectric constant here to get the velocity factors inside the vector network analyzers. For like this one, for SMA cables, you notice the dielectrics is a Teflon, right? So the Teflon, the dielectric decay value or the epsilon R, that is the 4.2. So that means we can get the velocity factors here. So that is 0.66. So you can see after we do the presentations, I will do the live demonstration. You can see how we can enter this velocity factors inside the network analyzers to get more precise calibrations of the port extension methodologies. Yeah, so it is quite important because if you input the wrong velocity factors, that means you will get the wrong informations of the Smith chart, even leverage to the wrong leverage to the VSWR test result. So the whole test result, the values will be wrong. Okay. Yeah. So that is the test procedures you can see here, so we can use the extended SMA cables to do the open short road calibrations and to use the port extension calibrations techniques to eliminate the residues effect. And then we can hook up antenna here to get a more accurate result like this one, you see? So you can see the path is very long because the cable is very long, right? So you can see the test results. You can see the VSWR, the resonant point will be at the dedicated 2.4 gigahertz because this antenna is the 2.4 gigahertz, right? And we can measure the VSWR here as well. Okay. Okay, this is the basic introductions of the network analyzers and the port extension techniques of these topics. So I will highlight some of the functionalities of our network analyzers so you can see here. So we can measure S11 and some parts of the S parameters for the vector network analysis, including the magnitude and the phase. Yeah. And the device on the test here, we can do this as the antenna, amplifier, filter, antenna cables, isolators, for example, like this one. But I need to highlight it because this is the spectrum analyzer, right? This is the RSA 5000 series network analyzer with the option and network analyzer options. So we need to use the tracking generator as the first one point, and the 2 port is the receiver port. Like to use this one as a network analyzer to get the VSWR test, right? Yeah. So it is quite simple, but not the fully network analyzer. Okay. Okay. So this is the basics, presentations of the network analyzers basic, and I have already introduced the port extensions methodologies of the calibrations, the techniques. Okay. So before we do the live demonstrations, any questions from your side? So don't hesitate to raise up your questions in our chatting area. Okay. So I will see some questions about this one. Okay. Any questions? Don't hesitate to raise up your questions in the chatting area. I can answer you. Yeah. Okay. Any kind of questions? Okay. If you don't have any questions, I will do the live demonstration first. Okay. So then we will go back to the question and answer sessions. Then we can explain more about your questions after the live demonstration. Okay. Okay. We will go for the next screen. So have you seen this screen? Okay. I will go for the demonstration. Okay. So everybody, you can see this one is a spectrum analyzers, that is RSA 5000 N series from the 9 kHz to the 6.5 gigahertz. So we call it as the multiple functionalities signal analyzers. So you can see the right-hand side. So you can see we have the general purpose spectrum analyzer, real-time mode, and the vector signal analysis. You can do some of the demodulated capabilities, such as the constellation diagram, the bit stream analysis, spectrum analysis, and the EVM analysis, because the constellation, you need to verify the error, right? And we also have the EMI, right? To do the EMI verifications. And the final one is the vector network analyzers, which we need to introduce today for this environment, right? So you can see this is a 4-quadrant part. You can see the left upper side is a Smith chart, right? The right-hand side is a polar chart. And the left bottom side is the S parameters. and the right-hand side is VSWR test diagram, right? Before we do the formal test, we need to do the calibrations by using this open, short, and load kit, right? Of course, this is our device on test. It is the 2.4 gigahertz Bluetooth antenna here, right? So now you can see here, this is the SMA cable with the adapters because the calibration kit is N-type. So we need to use these adapters to convert the N-type to the SMA type, okay? Yeah, so now we will do the calibration first, okay? Before the calibrations, we need to set up the frequency range and the swept point of this network analyzer, okay? So for this one first, we can press the frequency buttons because this 2.4 gigahertz antennas, so we can set the frequency range started by the 100 megahertz, okay? And stop the frequency, we can set as the 4 gigahertz, okay? Okay, then we go for the sweep the point here. Press this sweep the buttons. You can see the right upper side, we can see this sweep the points. We can adjust this as the 801. Why we need to set as the 801? Because the original 201 is less points. So I'm afraid of the less accurate compared to the 801, okay? But if you set for 1,000 points, that the calibration procedure, we need to spend much more time. So today I would do the demonstration more efficiently. So I just tune this as the 801. That is just makes sense. Okay. Yeah. Hope you can understand. Okay. So we can press the OK. Okay. So then now we can do the calibration procedures now. Okay. So we can press the measure setup here. Okay. So you can see the right-hand side of this screen. You can see this align, right? Align, press align. You can see the open, short, load calibration procedures listed at the right-hand side of this menu. So before this one, we can use the open, right? Open kit to hook up this terminal. Okay. Wait a second. Okay. After we hook up tightly with these terminals, we can press the open. Press. You can see the open calibrating. Now it's working. Oh, finished, right? Okay, then we release this terminal and switch to the short calibration kit. Like this one, short, right? Short kit. Calibrate it. Okay, then we press the short. Okay, finished. Release this kit and change the final one. This is load. This load is 50 ohms because it can match for average over 80% applications because RF microwave systems almost the coverage at 50 ohms, right? So we can hook up this 50 ohm, right? Okay. After this one, we press load. Okay, finished. So after we finish the open short load, we can press the down, right? Press it down. Oh, when you see the down pressed, you can see the central point, right? The point, the yellow point is at the central. That means we have a much better and good matching status and matching calibrated result. And you can see the S11 almost below the minus the 50 dB, right? That means we have a successful calibration result here. Yeah, it's very beautiful one. Okay. So then we will release this load and change to the device on the test. Okay. Yeah. So this is, we will hook up this antenna here. Okay. So we hook up this antenna. Okay. Oh, you can see here, right? Okay, we can use this amplitude to do the auto scale. Okay, auto scale here. Okay. So we can use the cursors, right? Marker here. Okay. So the marker, yeah. Okay. Move the markers here. Okay. Okay. So do some of the precise accurate. Okay. This is the VSWR resonant point, right? Oh, it's very, it is a little bit the deviations. You can see the value, a resonant point. Okay, it's a 2.36 gigahertz. Perfect. That means we have the error is very small and get the final result like this one, right? And we can see this Smith chart, right? We can press the marker. Oh, you can see here, that is the final, the 4 gigahertz, the final swept point at this one. So you can see this marker is located at the upper semicircle, right? What does that mean? That means it is inductive effect dominate, right? Why this is inductive dominate? It is quite simple. You see this one? This is the transmission line. It's very long, right? It's a very long transmission line. That means the inductive effect is dominate the capacitive effect, right? So it is quite simple concept. I hope you can understand. Okay. And this is the VSWR. You can press the marker. Okay, you can see it's a VSWR here is about 2.33. It is not very good because generally speaking, if the VSWR less than 1.5 is much better. But you know, this antenna maybe is not very ideal or professional. So it is a very simple and the cheaper one. So I think have some deviations and much worse performance, but no worry about that. So average speaking, the resonant point is very accurate. Then you can see that is 2.36 gigahertz. So yeah, that is very simple live demonstration about the port extension, right? Yeah. Before this one, we need to set up the, okay, I forgot to tell you about this one. Yeah, we need to set up this one as the unit 1, the 0.6. I have already inside this one, right? This is the velocity factors here, right? And this one length, you can see this 1 meters, 1 meters here. Yeah. Okay. So you can do some calibration procedures like this one. Yeah, you can see this one. Yeah, it's very long, right? So you can see the test result and every kind of to included the test parameters, included this one. Yeah. So it is a port extension, the parameters included this application and the calibration procedures. Okay. Yeah. You see, this is down to the 1.92 VSWR because we have already included the port extension parameters inside. So you can do some adjustment on the fine tune about this test result. Okay. So this is a live demonstration of the port extension technologies. Okay. I will switch back to the presentation slides. Okay. So we will go for the question and answer sections. Any other questions from your side? We can have furthermore discussions to do some discussion. Okay, it would be nice if the open show load buttons have the green mark after being performed. Okay, thank you, Andre. This is a good suggestions and feedbacks. we will feedback to the divisions or the business unit to match much more the feedbacks and to optimize this performance. Okay, thank you so much. Any other questions about this port extension technologies in today's presentation about the microwave component test challenges? Any other questions? Oh, Aaron, I don't have full calibration kit open source. Could you measure the VNA functions? Full calibration kit. You don't have full calibration kit? No. You need to have open short load 3. Cannot neglect any one of the 3 because the open short, that means we need to calibrate by the right-hand side of the Smith chart and the left-hand side of the Smith chart. And also we need to converge to a central point to have the matching point optimization. So the open short load are very important. We cannot neglect any one of the 3. So if we lack of any one of this one, you can get the completed the test result of the VNA. Okay. Thank you so much. Okay, Peter, that point. Thank you so much. Just right amount details about introduction to great live demo. Thank you so much. Thank you for your recognition. Any other questions from your side? I encourage you can raise up any kind of the test challenges when you do the real measurement at your lab. So we can have furthermore discussions when you have some challenges. Because from the RIGOL side, our major task is want to solve any kind of the pain point issues or the main requirement from the customer. So we are eager to solve your any kind of problems. Okay. How frequent I need to do the calibration? Okay, it's a good question. If you turn off the machine, when the next time you turn on the machines, you need to recalibrate it. Okay. If you calibrate this, but the machine goes on and keep power on for 24 hours or just 1 week, yeah, you don't need to do the calibration theoretically. But if the machine inside has some residual effect in the temperature drift about some parameters, I suggest after 3 days, you need to recalibrate it. Okay? Thanks. Would like to see any EMC webinar in the future? Okay, no problems. For the past 2 years, 1 year, we every year we have the EMC topics. Yeah, so don't worry about that. We can arrange the similar topics in the futures. Don't worry. Yeah, and you can feedback to our the regional's office and to have some feedbacks to our headquarters. Our marcom guys will coordinate all the topics in the futures and to follow your steps to have to satisfy your requirement. Okay, thank you. Any other questions, everybody? Okay, thank you so much. Yeah, today we have a very completed, comprehensive presentation. So thank you so much to join this webinars, and we hope that we have by month webinars and the topics in the end of June. So welcome to join this regular webinars at the end of the June time frame. So we will invite more customers or the partners to join these webinars to discuss for furthermore techniques of the both for the microwave or high-speed digital. Okay, thank you so much to participate in today's RIGOL's webinar. Thank you so much. See you then. Bye.